Okay, let's do some more practicing on circular motion. Let's take a look at the question on slide 10. Let's take a look at this question. You can swirl a ball with a string in a vertical circle, right? So in that case, the ball is in a circular motion. And then if we know that the speed of the ball at the bottom is 5 meters per second, what is the tension in the string? Okay, so let's take a look at it. What we have been doing is to still use Newton's laws, right? Newton's laws of motion to analyze any circular motion. Okay, you still set up Newton's second law in x and y direction, and then I would put the acceleration, centrifugal acceleration. You're going to draw the centrifugal acceleration if you see something is moving in a circular motion. You draw this centrifugal acceleration toward the center, and then you set up your x and y. I would always set up my x and y so this centrifugal acceleration is in one of these axes, because I don't like braking acceleration. I prefer braking forces. And once you set that up, you still set up Newton's second law, and then the centrifugal acceleration is just going to become your ax or ay, depending on which one you call x and y. But the steps are still the same as a straight line motion, a problem in straight line motion. Okay, so let's do that. Let's use this in this question. So if I draw a figure diagram of the ball at the bottom, okay, so what do we get? I would get gravity down, and then tension up, okay? So this is what happens at the bottom. The tension is up. So a lot of people, they will make this mistake. Oh, so in this case, tension is the centrifugal force. So I would just do tension equals m v squared over r. No, tension is not the centrifugal force in this case. You still need to set up Newton's second law to find out which force is the centrifugal force, or sometimes it's a combination of forces to be the centrifugal force. And we actually have seen that in the previous questions we did. Friction force can be centrifugal force, normal force, and tension, and even a component, only part of the force is a centrifugal force. So sometimes it's not that intuitive to identify, oh, this or that force is a centrifugal force, okay? The best way is to draw the Freiberg diagram, set up Newton's second law, you know which force is the centrifugal force. So I draw, this is the Freiberg diagram, nothing in x direction. If I want to set up Newton's second law, I'm going to still set up Newton's second law. So all I need to do is just set up Newton's second law in y direction, right? So net force in y direction, all the forces in y direction, that's going to be equal to A m a y. How many forces in y direction? Tension and gravity. Don't forget gravity. Gravity is still there. So I'm going to do tension minus gravity, because gravity is down. I'm going to call it negative. So this is going to be the net force in y direction. Now, what about the acceleration? This is the center, right? The center is here, say. So the acceleration, centrifugal acceleration is in that direction, okay? So I know there's always a centrifugal acceleration toward the center when something is in a circular motion. If I call this vertical as the y-axis, as we usually do, then that's going to be the ay I plug in, and it's up. So I'm going to use just v squared over r. So this is the centrifugal force, right? So we just call m times centrifugal acceleration centrifugal. Now you see that which force is the centrifugal force? Well, strictly speaking, not one of them is a centrifugal force. It's actually the difference of them. This combination is a centrifugal force, right? So centrifugal force is not a new type of force, only comes from a certain agent, as we emphasized earlier. Centrifugal force is totally, it's an effect on this, it's just a name for this net force on this object, which towards the center, and keeps this object in circular motion. Centrifugal force can be any force, can be a component of some force, and can be a combination of some forces. Sometimes the sum, sometimes the difference, okay? In this case, is the difference between these two forces is the centrifugal force in this case. But I don't need to worry about that. I don't need to figure that out before I set up this equation. I always set up Newton's second law, because if anything moving, right, they must obey Newton's laws of motion. I set up Newton's second law, whatever I have on the left, that's going to be the centrifugal force, right? Because I have mv squared over r on the right. This is the equation for the centrifugal force, okay? So in this case, you shouldn't say tension is the centrifugal force. That's a very common mistake people make, okay, especially on the test, okay? When they say this, I have the tension toward the center, so that's just going to be centrifugal force. But gravity is going to cancel some of that, right? So the net force in this case, it's the difference between them. That's the effective centrifugal force toward the center. Once you have set this up, then you see that's going to be easy. You just rearrange this equation, you can find the tension, right? Because we have all the numbers we need. The mass, 3 kilograms, the length of the string, in this case, just the radius of this circular motion. And the problem says the speed of this guy at the bottom is just 5 meters per second. Okay, so now you can pause the video, finish this algebra. So you will just get tension. You rearrange this equation, you will get this, right? And then if you look at this equation, this is not intuitive at all, right? How do I know that the tension equals gravity plus centrifugal force? Okay, does that doesn't look very intuitive to me, but that's a conclusion from Newton's second law. You always set up the law and then go from the law. You don't figure things out intuitively, okay? And then if you put all the numbers in, the velocity is this, right? The mass is 3 kilograms, and then the radius, in this case, it's going to be 0.4 meters. You put all the numbers in, you will get 216.9 newtons. All right? So this is this question. Now let's take a look at the next question. So it's the same motion, the ball attached to the same string, okay, moving in this circular motion. Now I want to find the tension in the string when the ball is at the top. Again, you don't know what this tension, don't just say the tension, because the tension is toward the center, the tension must be the centrifugal force. You have to take into account all the forces. So at the top, this is what I would draw. Tension down, right? Gravity also down. So this is the center. You don't draw centrifugal force. You don't draw that. Centrifugal force is not a force you should draw in the Freiburg diagram. No, you don't. You still draw all the normal forces we see. And then once you figure that out, you set up Newton's second law, you can find out what force or what forces are the centrifugal force. That's how we find that. So you never draw centrifugal force, otherwise you will have 3 forces, okay? You're going to confuse yourself. But I would draw the centrifugal acceleration, okay? But I'm not going to draw the centrifugal acceleration on this guy, right? Because again, I don't want to confuse myself. I would just draw acceleration toward the center, okay? So that's always, that's going to be the direction of the centrifugal acceleration toward the center. But that's an acceleration. I'm not going to draw it with these forces together. Otherwise, it's going to confuse me, right? I may write this A in the force equation. Now let's set up Newton's second law. So you see, I have 3 vectors. They're all down. So if I still pick all the up as a positive, as we usually do, then I would have like 3 negative signs. So why don't we, in this case, I have all the vectors down. Why don't we just assume, okay, I'm just going to call down positive. Because there's nothing wrong if you call down positive, right? Because up and down, which one's positive? That's totally arbitrary. If I do this, then let's see, how do I set up Newton's second law? I would still do this. Net force in y direction equals all the forces in y direction, that must be equal to mass times acceleration in y direction. How many forces in y direction? 2. And if I go down positive, so both of them are going to become positive, so I should have T plus mg. That's going to be the net force in y direction. What is acceleration in y direction? If this is the y-axis I call, so AC, the centrifugal acceleration, is in the y direction. So that's the acceleration I plug in y direction. The acceleration in y direction is not 5 meters per second squared given the problem. It's this expression because this is a centrifugal acceleration. This ball is in a circular motion. Now you see that if I ask you, what is the centrifugal force? In this case, you shouldn't just say tension. It's actually, again, the combination of these two forces, but this time it's the sum of these two forces, which is the centrifugal force. And then, in this case, is the difference between them. So this is not intuitive at all. You have to start with the laws. You can identify which force or which forces are the centrifugal force. Sometimes it's even a combination of like many forces, all right? Then you see, once you set up this equation, you can go ahead and solve this equation. Because this is still Newton's second law. You rearrange this equation, you can find the tension, and you already have all the numbers. In this case, the problem says the speed at the top is going to be 4 meters per second, right at the top. So you put all the numbers in, what do you get? You just get T equals mv over square over r minus mg. Again, look at this conclusion. This is not intuitive at all, right? By staring at this problem, there's no way you can figure out that, oh, tension equals centrifugal force minus gravity. Okay, how is that true? You set up Newton's second law. Everything is clear. You don't even need to draw the conclusion based on your own judgment. You don't need to come up with your own theory. You just do the math. It's going to tell you everything. You put all the numbers in. What is the number you got? This is the number I got, 90.6 newtons. Now let's take a look at the next slide. What is the minimum speed of the ball at the top to complete the circular motion? So if you do this experiment, if you have ever done this, right? If I want to swirl a ball in the vertical circle, I know that I have to swing it, at least with a certain speed so you can reach the top, right? If you swing it at a very slow speed, right? It's not going to reach the top. It's going to just drop at some point. So there is a minimum speed of the ball in order to complete the circular motion, right? I know that if I swing too slow, it's not going to go to the top. So how do I find this minimum speed? Okay, so yes, that's from my experience. I understand that's what happens when I swirl it with a low speed. But how do I find the minimum speed? How do I find the value? You have to do math. You have to use a theory. So there's no way you can figure that out intuitively. So I have to convert this problem to a physics problem. So I can use a law in physics that I can set up an equation and then find the value. So now let's think about this. So if this ball wants to complete the circle, so it wants to reach the top, but at the top, this is always true. This is always true. So now let's write it down and then let's take a look at how do I find the minimum speed for the ball to complete the circle. Say, okay, I'm swirling it with a very large speed. Of course it's going to reach the top. It's going to complete the circle. Now I'm going to do an experiment. I'm going to reduce the speed a little bit, okay? And then it can still complete the circle, okay? It can still complete a circle with that speed. If I reduce the speed a little bit, and this equation is still true at the top, right? Because this is Newton's second law. And if it's in a circular motion, the centrifugal acceleration is this, and then I still set up net force equals mass times acceleration in y direction. So this must be still true. If this is still true, that means these two numbers I calculate on both sides, they should still be equal. But I just reduced the speed a little bit. So that means this number on the left must also go down a little bit automatically in order to satisfy this equation, satisfy Newton's second law. Now let's take a look at these two numbers. How can this number on the left side become a little bit smaller, so it's still going to be equal to this number on the right? M times G. No, M times G is not going to get smaller, right? Because mass is a constant. Little g is always 9.8 on the Earth. But tension, well, okay, tension, there's no a certain value for tension in a string, right? You can pull a string really, really hard, and then the tension is going to be very, very high. So the tension actually can vary. We know that the tension is not going to be a constant in a certain string, right? So this tension is going to get a little bit smaller if you swing this ball at a smaller speed. So that means that the string is just going to get a little bit less tight, okay? Because the tension gets smaller. And everything is automatic because everything must satisfy Newton's second law. Everything must obey Newton's laws of motion. Now, okay, now if you keep reducing the v, the velocity on the right, then this guy must keep going down. Because again, if you want this ball to complete this circle, it's going to always satisfy Newton's second law at the top, right? And then because the centrifugal, it's still in a circular motion, centrifugal acceleration is still v squared over r. So you keep reducing this v until we reach the minimum value so that it just barely makes to the top. That's the minimum speed. So how do I find that value? If this guy has reached the minimum, that means this value on the left has reached the minimum. And the mg is not going to change at all. So that means the tension has reached the minimum at the minimum speed. What is the minimum value of a tension in a string? Or what is the minimum value of any force? Well, that's going to be 0. Right? You can't have a force lower than 0, right? Sometimes we say a force, when we do the algebra, we would say like a force like -5, +5. That's when we mean the direction. If you tell me a force is -5 newtons, I would ask you, what do you mean -5 newtons? I don't understand that, right? You may say, oh, I mean it's in the direction opposite to the positive direction I assumed, but the value is still 5 newtons. So the minimum value of any force is going to be 0, right? Because it's a vector. When I say the value of a force, that's magnitude. So the minimum speed, okay, it's just going to occur when the tension has reached 0. So that's when the ball can barely make it to the top and complete the circle. But any speed lower than that, this equation is not going to be satisfied, right? Because the t has already reached the minimum. It cannot go any lower than 0. So that's the minimum speed for the ball to complete the circle, right? So once you have figured that out, you see the algebra is very easy. If the t is 0 and this equation is still true, remember you still want the ball to complete the circle. And this equation is still true, you just solve for this, solve this equation to get the v minimum, right? And that's going to be very simple. Okay, now you can pause the video and finish this algebra. All right, so if the v equals 0, then you will get, at the minimum speed, this is going to be the second law. The tension is 0, and then you solve this, the algebra is very straightforward, you just get this. Okay, and then you can plug numbers in, right? Little g 9.8, the radius 0.4, that's still the length of the string. You put them in, you get 2.0 meters per second. Okay? So at this point, I usually get this question a lot. A lot of people, they would ask, well, how would I know that the minimum speed occurs at the tension equals 0? Right? This doesn't look intuitive to me. A lot of people wouldn't be able to figure that out. Like for me, like the first time I saw this question, I wasn't able to figure that out, okay, unless someone taught me. So I realized, oh, that's nice. You just need to still use the Newton's second law, set it up, and see how these variables change in this equation. And then, if you want to find the minimum value on the right-hand side, try to see if you can find the minimum value on the left-hand side, okay? That's how you learn It's a learning process. So a lot of questions in physics, the first time you see them, you don't know how to solve them. That's very common. That's very common. That's why you are learning. That's why you're taking this class. That's why we're practicing. That's the purpose. Once you have practiced this question, next time, right, you see a problem and the problem asks you to, I want you to find the maximum value of this, or I want you to find the minimum value of that. Maybe I can still set it up using a law I have learned. And then if I want to find something, the maximum value of something on the right, try to see if you can figure out the maximum value on the left. Or if I want to find the minimum value of this thing on the right, try to see if you can find the minimum value on the left. That's what I learned from this question. So next time when I see a similar question, I know what to do. That's what we're learning. That's a learning process. Okay, so don't feel like really bad. Oh, there's no way I can figure this out. When I solve this problem myself, I cannot even figure that out myself. Okay, so that's the point. That's the point. That's why we are practicing. We are solving different types of questions. Even though I know, okay, I remember what you said. Always Newton's laws. If I see any problem in circular motion, I just set up Newton's second law. But you may need to manipulate this equation, the laws, a little bit differently when you see a new story. You may need to convert real life problem to a physics problem. So that does require a lot of practicing. That is what we are doing in class and homework. Okay? All right? So now let's take a look at another question. So this is the question, on the last question I want you to, again, practice circular motion. This is the question on slide 13. A model airplane of mass 0.75 kilograms flies in a horizontal circle. So something flies in a horizontal circle, right? At the end of the 4-meter long control wire, okay, forces exert, so the problem already shows you all the forces on this airplane, this model airplane. Gravity down, right? The tension from the wire on this plane, and there's a aerodynamic lifting force on this plane as well. So 3 forces on it, and the problem also gives you all the directions. Now let's see. So let's draw it out. I have these 3 forces on, so it's just an object to me, right? I don't even need to draw an airplane. Gravity down, there's a tension in this direction. I can still use the normal x and normal y. So the tension makes an angle theta with the horizontal, okay? And this is the angle theta given in the problem. And then there's also lifting force, aerodynamic lifting force in this direction, which makes angle theta with the vertical, okay? We call it F lifting. So these are the 3 forces, okay? So the problem already drew this Freeburg diagram for us. That's nice. What are we finding? We want to find the speed of the airplane if the tension is 10 newtons and theta angle is 20 degrees. So I have these 2 numbers from the problem, right? Tension is 10 newtons, theta angle is 20 degrees. I have something in circular motion. From all these problems we have practiced, it's still going to be Newton's second law. I just need to set up Newton's second law in x and y directions and then manipulate these 2 equations. If I want to find speed, the centrifugal acceleration will have the speed in that expression. So this looks promising, so let's do that. So I can still use the normal x and normal y, so I would do the net force in x direction. It's going to be all the forces in x added together. That's going to be max. And then do the same thing in y direction. You see, we're always setting it up with the same law in this part. That's what we are learning. That's what we learn in physics. I can always use the same law, the same theory, solve different problems. The x direction, now let's see. So gravity is already in y direction, and then, so I don't need to break gravity. Centrifugal acceleration, what is a centrifugal? So it's still moving in a horizontal circle. So where is the center? So you should be careful. Some people may make this mistake. The center is still here. So centrifugal acceleration is still in this direction. It's not in this direction. Some people may think, oh, centrifugal force in this direction because that's the string. It's not. Because if you assume centrifugal acceleration in this direction, then the center is somewhere here. If the center is somewhere there, then it's not going to be a horizontal plane, right? It's actually going to be moving like this, okay? So it's going to be moving like this. If it wants to move in a horizontal plane, you see that it's attached to a string, but it's still moving in a horizontal circle. So the center is here. So it's still here, not here. If it's there, you're assuming the ball is moving this way, right? If this is center, you're assuming this airplane is moving this way. But this is not, right? It's still here. So it's a little bit hard to visualize, but the problem says it's still moving in a horizontal plane, horizontal circle. So this is the center somewhere. This is not the horizontal. So I'm still call the horizontal as my x-axis because I don't like breaking accelerations, right? Even though I could, but I just prefer breaking forces. I'm more used to breaking forces. So I'm going to still keep this as the x and this as the y. So I need to break this lifting force and the tension, these two forces. And then you see that if I break these two forces, I will have both of the x component in that way. So in x direction, I will have two x components that way. I would also have the acceleration that way. Why don't we call this x direction? So I don't like negative numbers. I know a lot of people, they're afraid of negative numbers. So let's just make that x. So everything is going to become positive in that direction, in x direction. Nice. Now in y direction, I will have this, right? So this guy also has a y component, you break it. This guy has a y component, you break it. So you will have one component up, two components down. So, and that's the forces you put in this y direction. Okay, so that's gonna be our goal. We're gonna break every force into x and y directions and then put all these components in this and x components here, y components here, and then rearrange this equation, manipulate these two equations so I can get v, because v is gonna be in the centrifugal acceleration equation. All right, so now let's see. First of all, let's break these two forces. Let's break these two forces. So I'm going to draw a new diagram for each force. That's what I would do in on a test. I'm not going to draw everything on the original diagram because that may get really messy. So it's going to confuse myself. I want to keep everything very clear. So why don't I draw another one? So let's draw this F lifting. So the lifting force has an angle theta with the horizontal, and okay, we decided to call left positive. So draw these two components. So how do you find these two components? Then this is going to be the x component, right? F lifting x. And then this component is going to be the y component. And then how do you use the theta angle and this F lifting, this symbol, to write them? Okay, so that's going to be the two components you plug in. Do the same thing for the tension. Now this is the tension. The tension at the theta angle is the horizontal. Now break it into x and y. This component, it's going to be Tx, and then this component is going to be Ty. And then this is still T. So I can also write Tx and Ty in terms of T and theta. So then you can put all these components on the left hand side, x components here, y components here, but don't forget gravity is another y component and it's down, so you should assign negative sign for gravity. All right, so what do I get? So I will get this at the end. The lifting force in x direction, positive. The tension in x direction, positive. And that's everything in x direction, so I can write the equal sign and mass. What is the acceleration in x direction? It doesn't have any normal acceleration in that direction because it's not moving in that direction, but the centrifugal force is then in that direction. If you call this is your x-axis, you would put the centrifugal acceleration in that direction, so that becomes your ax. So my ax is going to be this. I'm still using Newton's second law. I'm not using a different law, but the acceleration in x or y direction can be the centrifugal acceleration, depending on which direction you call x or y. Now do the same thing in y direction, so I would have lifting force in y direction positive, tension negative, right? Tension y direction negative, and gravity negative. Okay, all the forces in y direction. What is the acceleration in y direction? I'm going to have m times ay. Well, it doesn't have any normal acceleration in y direction because it's not moving. The center is not on this y-axis, so there's no centrifugal acceleration. Okay, so there's none at all. There's none at all, so I would put a 0 right inside. Now you see that I can solve for tx and ty because I already know t and theta. So these two guys, they're going to become a number for me. Don't forget what we're doing. We're trying to solve for this v. We're trying to solve for this v. So all we need is going to be the f lifted x or f and these two numbers. And these two numbers, you can write them as the lifting force times theta sine or cosine. So you don't know this lifting force, but you have the theta angle. But if you put this f lifting and sine cosine theta in these two equations, how many unknowns do you have in total? You're going to have f lift, you're going to have v, and that's it. Okay, don't be afraid of so many symbols. At the end, only these two symbols are the variables you don't know. Everything else, like theta, tx, ty, mg, you will get all these numbers. So I have two equations and two unknowns. I'm confident I can solve them. This is the right direction. I just need to work out the math. All right, so I just need to work out the math. So that's what we're going to do. So the algebra may take me some time to finish, but this is the right direction. I'm confident this is how I'm going to solve this problem, because mathematically, if I have two equations, two unknowns, I can always solve for these two unknowns. All right, so now you can pause the video and then find these four components, put them in. Some of them are going to be numbers, some of them are going to be expressions, that's fine. Rearrange this equation, you will be able to find the v. All right? Let's see, how do I find this component? So this ty, if this is theta angle, so ty must be t times sine theta, right? And if this is theta angle, tx must be t cosine theta. So that's because that's adjacent and ty is opposite to theta. What about this lifting force? If I break it into x and y, the x component is going to be this side, which is also equal to that side, so that's a right triangle. So that's going to be opposite to the theta angle. So lifting force sine theta. What about y component? Y component, it's adjacent to the theta angle, so that's going to be f lifting force cosine theta. Now let's put all these four components in these two equations we just found. What do we get? I will get f lifting force, x component, it's sine theta. That's what I said many times. Don't remember x is always cosine, y is always sine. Totally depends on what angle you get from the problem. Tx, t cosine, equals mv squared over r. And then the lifting force in y direction cosine theta, that's what I figured. Now the tension in y direction T sine theta mg equals 0. So you see the only two unknowns you have in these two equations is going to be this as your x and this as your y. Everything else you can find a number. T is a number, sine cosine theta is a number, m is a number, g is a number, r, okay, so the r is a little bit tricky. What is the radius of this circular motion? It's not the length of the string in this case, right? Because as I said, this ball is not moving this way, okay? This is the other end of the string. If you assume this is the center, the ball must be moving this way. But no, the ball is still moving in a horizontal circle. So right at here, that's the center, right? So you have a right triangle here. So let me draw it out. What is the, this is the string, this is the other end of the string, this is the airplane, this is the center. If this is the center, this is the radius. How do you find that radius? You have the length of the string is 4 centimeters, yes, but that is not the radius. The radius of the horizontal plane. So it's moving still in the horizontal plane. How do you find this r? You're going to still do a trick, right? You have an angle here, theta. So how do you find this radius? If you have this theta angle and this r, you're going to still go ahead and use this right triangle, right? So r is going to be equal to 4 meters times sine or cosine? Cosine theta. That's going to be the r you plug in, okay? So I'm just solving for x and y using these two equations. This is going to be my x and y. How do you solve for x and y with two equations? You substitute. You just write x in terms of y, or write y in terms of x using y equation, and then plug that into the second one. You will get rid of one of these unknowns. You will have y equation for y unknown, and then just go ahead and solve for that. Okay? So that's how you solve for two unknowns. Now let's see. But in this case, it's a little bit easier because you can actually solve for one of the unknowns using y equation. That's one. Because if you look at the second equation, you will get the lifting force. But what am I saying this? Once you get these two equations, you should be confident. This is how I'm going to solve for these two unknowns, right? The algebra can be a little bit complicated. I may need to manipulate these two equations, but this is how I'm going to solve them. Two equations, two unknowns. I can always solve for these two unknowns. So the lifting force in this case, you rearrange that, you can get this divided by cosine theta. And you do have all the numbers you need, right? You don't have v in this equation, so you can solve for F lifting. If you get this equation also has like v in this equation, doesn't matter, right? You just keep this expression in terms of v and then plug it into the first equation. You get rid of this variable x. You will have this equation owning in y, v, right? And then you go ahead and solve this equation for v. Then you go back solve for that. That's always how we solve two unknowns, right? How we solve two equations for two unknowns. Now this number I got, if you plug all the numbers in, this is going to be 11.6 meters, right? And then you can go ahead and plug this lifting force in the first equation and solve for v, right? So if you solve for v, what do you get? You will get v equals the lifting force sine theta plus t cosine theta divided by m and times r. And r is this 4 meters times cosine theta. And don't forget the square root. Right? So that's going to be a complete expression for v. Again, I always plug all the numbers in at the end. When I do the algebra, I carry all these symbols, because I may be able to cancel some symbols. Now you put all these numbers in, what are you going to get? you are gonna actually get 8.2 meters per second, not second square. So that's how we solve this problem, all right? Now let's take a look at the last slide. So on the last slide, I summarized all the common forces we're gonna see in this part. So let's take a look at them. Gravity is actually the simplest force because gravity, we have a very nice equation for gravity, m times g. And the direction is always down. So that's why gravity, when I draw for a diagram, gravity is always the first force I draw because it's very easy, it's always there, and it's always down. The value is always mass times 9.8. Normal force is another common force we see in this part. Normal force always comes from a surface. So if you see an object on the surface, you may need to draw a normal force. And the normal force is always perpendicular to the surface. So it's not always straight up, don't make that mistake. A lot of people will make that mistake. And it's not always equal to gravity. Because we have seen some simple cases when you have an object, right, on this flat horizontal surface. And then if you draw these two forces, you will have gravity down, normal force up. But this is not a law, a universal law that I should remember. Always true. Normal force is always up, it's always equal to gravity. No, this is actually a very, very special conclusion. We have seen this a lot, but that doesn't make it a law. Doesn't make that always true for every question I see. So don't make that mistake on the test. When you see a normal force, draw it out. Draw all the forces on this object. You can see the direction and the magnitude. The direction is always perpendicular to the surface. So if it has we have done that, right? If it's on the incline, it's going to be perpendicular to the incline. It's not going to be straight up. Friction force is another force that can come from a surface. And the direction of the friction force, it's always parallel to the surface. But again, that doesn't make the direction unique. For example, if I have a surface like this, parallel to the surface, the friction force can still go this way, or that way, right? Depending on the motion. So how do you find the right direction of the friction? It's always going to opposite to the motion or attempted motion. If it's moving, then it's kinetic friction, so it's opposite to motion. If it's not moving, there might be still a static friction on it, and the static friction force is opposite to attempted motion. The object wants to move, say, in this direction, so the static force is going to keep it from moving, so opposite direction. So that's how you find the friction force. So normal force and then friction force, they are always from a surface. They're always from a surface. Another force we usually see in this part is the tension. Tension, it's always from a string or rope or cable. You see these things in the problem, you should draw tension. And the tension is always parallel to the string. Okay, if you have a string this way, so it's going to be parallel to a string, it's going to be in that way, because it comes from the string. And the direction is away from the object pulling it, right? So if this is the case, the object is pulling the string that way, then of course the string is pulling the object in this way. So that's why it's always away from the object pulling it. Okay, so that's actually action and reaction, right? Object pulls it that way, the string pulls the object that way. Or you can say, if the string pulls the object this way, the object is pulling the string that way. Okay, so this is how we find the common forces we see in this part, the direction and the magnitude. We also have like some empirical equations for friction forces, but to predict normal force and tension, everything else, you're going to set up Newton's laws, and then you manipulate these laws, you can get things you need. Okay, so I'm going to stop here for this video.